Welcome back to Math 104. Suppose that a true-false exam with 10 questions is randomly generated, so that all possible answer keys are equally likely. We can ask, what is the probability that the correct answers to the first 4 questions are either all true or all false? When you thought about this at the end of the last video, you might have realized that this problem is actually equivalent to the previous one about baseball teams playing one another. Even though the exam here has 10 questions, we are asking only about the first 4 questions. Just as in the previous problem involving baseball games, although the World Series might last for 5 games or 6 games or 7 games, the question we asked there only had to do with the first 4 games. Just as there were 16 different 4-letter words consisting of Y's and M's, there are 16 different 4-letter words consisting of T's and F's. 16 different possibilities for what the sequence of correct answers could be to the first 4 questions. Of those 16 words, there are only 2 that count towards our event, namely true, 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 and false, 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 false. Therefore, the probability that we're looking for equals 2, these 2, out of 16, which again is 1/8 or 0.125. There is a 1/8 chance that just by chance, the first 4 correct answers on your true-false test really will be either all true or all false. It's helpful to see another way of doing this, and another way of thinking about it. I can well understand if you're nervous about our ignoring the last 6 questions and looking only at the first 4 by this method. Here's another way of thinking about it that really uses the multiplication principle very explicitly. This is a 10-stage process, so I have 10 copies of the number 2 that I'm multiplying together to count up in the denominator the number of different possible answer keys, the number of different possible sequences of what really are the correct answers on our true-false exam. That's 2 to the 10th, which is 1024. Out of all 1024 different ways that this true-false exam could be put together, let's count how many start out true, 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 or false, 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 false. Using the thought process of the multiplication principle, the correct answer to the first question might be true or false, and it still counts toward our event. But once we know what is the correct answer to the first question, the second question must be the same, and similarly the third question, and again the fourth question. However, once we get up to the 5th question, we're back to being able to have either true or false as the correct answer, and we're still talking about an exam that starts out with its first 4 answers either all true or all false. So there are 2 possibilities for the 5th question, 2 for the 6th, 2 for the 7th, 2 for the 8th, 2 for the 9th, and 2 for the 10th. We can go about simplifying this, and we discover that there is cancellation galore. All manner of 2's cancel from one another in numerator and denominator, and sure enough we are left with 1 over 2 cubed, which is 1/8. You might be more comfortable with this approach, which directly acknowledges that there really are 10 stages in the process of putting together a 10-question true-false exam. Understanding this computation and how it works out has some practical consequences that are worth understanding. Suppose, for example, that you are taking a true-false test, and you look at the first question, you think that the answer is true, so you write down true. You look at the next question, you think about it, you think that the answer is true, so you write down true. You get to the next question, you think about it, again you think that the answer is true, so you write down true. Now you get to the 4th question, again you think the answer is true, and perhaps you're starting to get nervous. If you had thought genuinely that the first 4 correct answers were all false, you might get nervous as you got up to that 3rd or 4th consecutive false. Ask yourself honestly, if that happened, would you second guess your answers? Would you be tempted to change them because you couldn't believe that a randomly constructed test would really have 4 true answers or 4 false answers in a row? Our computation that this sequence of 4 trues in a row or 4 falses in a row will happen 1/8 of the time suggests that actually it is entirely reasonable to think that a randomly constructed test would really have 4 trues or 4 falses in a row. Another way to think about it, to make it really concrete, is to think about an ideal data set of 80,000 students taking the exam. Imagine, for example, a school district is administering this exam, and 80,000 students are taking it simultaneously. If all of their exams are randomly constructed, so that every possible sequence of trues and falses is equally likely, then of those 80,000 students, 10,000 of them have a version of the test in which the correct answers to the first 4 questions really are all true or all false. When you think of it as 10,000 whole people out of 80,000, it becomes much more concrete that you could very easily be one of those 10,000. So what's the conclusion? If you really think that the first 4 answers really are true, or that the first 4 answers really are all false, don't second guess your answers. Leave them the way they are. On a true-false exam with 5 questions, what is the probability of getting a perfect score just by guessing? Let's first think how to represent the outcomes. We can certainly represent each outcome as a 5-letter word in a 2-letter alphabet, because there are 2 possibilities on each question. But the 2 possibilities that we're really interested in this question are right versus wrong. So let's think about 5-letter words consisting of R's and W's rather than T's and F's. You could work with T's and F's if you wished, but I think it's easier to work with this notion of right versus wrong answers. In particular, a perfect score corresponds to one and only one of our 5-letter words, namely RRRRR, all correct answers. Overall, how many different possible words are there? There are 2 to the 5th, that is, 2 times 2 times 2 times 2 times 2. This is a 5-stage process with 2 possibilities at each stage, so there are 32 different possible such words. That means that the probability we're looking for equals 1 out of 32. This is less than 4%, so if your goal is to get a perfect score on a true-false exam with 5 questions, it would be a very good idea to study instead of just guessing. As a lead-in to our next topic, we ask, what is the probability of getting at least 4 answers correct on this 5-question exam just by guessing? We run into a difficulty here for the first time, and it's really important to understand this. When trying to answer this question, students are often tempted to apply the multiplication principle. They argue that there are 5 slots for the experiment. That's true if we're counting up all the outcomes in the experiment. There's a slot for question 1, a slot for question 2, a slot for question 3, etc. It's understandable to try to count how many outcomes are in this event by writing numbers into slots, but let's see what happens. For question number 1, there are indeed 2 possibilities. In order for our event to occur, of getting at least 4 correct, that first answer could indeed be right or wrong. The trouble is that if we then attempt to write a number, a single, unambiguous number, into the slot for question 2, we don't know what number to put there. If we got question 1 right, then we could afford to get question 2 wrong, and it would still count towards our event. That would inspire me to write a 2 right here. But what if the answer to the first question turns out to be wrong? That would mean that I can't actually have a 2 here. I would have to have a 1 here. If I got the first question wrong, I would have to get the second question right in order to count towards the event that we're discussing. This means that I don't know what number to put here. I don't know whether to put a 2 or a 1 without doing some kind of case-by-case analysis. But that means that this counting problem is not a job for the multiplication principle. There is not a single unambiguous number that we can put in the slot for the second stage for question 2. Similarly, there isn't one unambiguous number that we can put in this slot for question 3. We're going to have to think about it in a different way. We're going to need a more direct way of counting how many outcomes contribute to this event. Before going on to the next video, find the probability of our event, that is, of getting at least 4 answers correct by guessing on this true-false exam with 5 questions total, and do it by writing out all the words that contribute to this event. For example, we already know that RRRRR contributes towards this event. This is the one way of getting a perfect score. Think of what all the words are that have 4 right and only 1 wrong, and then think what that tells us about the probability of getting at least 4 correct on the exam just by guessing.